The next topic is digital signature. Here the problem is that of authentication. So M sends a message and the recipient wants to be sure that it is really sent by M, a bit like we saw with the Mac before. But here we can use asymmetric cryptography where we exchange the order of the keys here. The message M is signed using the private key. So the signature consists in computing something similar to a tag. It's not called a tag, but it's the same except that we use asymmetric cryptographic mechanism. It's called a signature, S. Then I send in the clear the message and the signature. And in order to verify it, when I receive the message, I recompute the signature S of the message M. That should sound familiar. That's exactly what we did with a tag here. Except now, the key I need to verify is public. So that is, of course, much more convenient. If the bank sends me a message and I want to make sure it does come from the bank, then I can verify it by using the key of the bank, which is a public key that is easier to distribute because it's the key of my bank and there's only one for the whole world here. So that's very similar to what we had with a tag, except so it provides authenticity and integrity. Same thing we saw with Mac a few minutes ago. But also more, because here, in fact, since the verification is public, it provides public verification. Anybody can verify that the message was indeed signed by the owner of the private key, including justice and the police. And so it's not a private affair, but one that can be verified by multiple people. So it's a much stronger authentication mechanism. RSA is also used with this purpose. We saw RSA for providing confidentiality, and this is used, for example, for creating session keys in hybrid cryptography. RSA is also used for signatures by using the fact that decryption and encryption commute with RSA. Let me explain. If I have a message to send and I want to provide some authentication, so for example, I am the bank, I sign the message with a private key, I am the bank, or I am Apple or Microsoft providing some software, and you want to be sure that when you receive the software, it is truly the software that was created by the provider of your operating system. So, because of course, one way to attack a system is if you can provide corrupted software. So I sign the message with my private key, which of course should be very, very secret. I send it, and when you receive it, you will recompute the signature, but using the function which we call E, encryption, with the public key K here. Here, I said decryption and encryption. In fact, we should give different names, but it turns out for RSA, this is exactly the same function I used when I was decrypting a message here. And here, it means that if I decrypt, RSA, like any encryption mechanism, to be correct means that whenever I decrypt something that someone has encrypted, I should recover the initial message. So the correctness of an asymmetric cryptographic system means that the combination D of E gives the identity here. Now it turns out that those two operations commute because they are exponentiations. If we remember the details we saw a minute ago, we put something to an exponent here. So whether we do it in this order or in that order, it gives the same, which means that if I change the order, if I first apply the decryption function and then the encryption, I will obtain exactly the same thing. So if we reverse the order of which it was intended to use RSA, we obtain a signature scheme. And the signature scheme here, of course, has the very interesting property that the verification key is public. In fact, that's probably one of the most interesting properties of RSAs and similar asymmetric cryptography schemes. Like for Macs, the issue of the security of such a scheme is forgeability. Is it possible to recover the key, in that case the private key here, by seeing a number of MS messages? And the answer is no, if the underlying crypto system is secure, which means in particular, in this case, if the key here is very large. In practice, however, we don't produce a message, we don't produce a signature that is as long as the message. If we take this verbatim as I presented, we take the message M, we apply the function D, which is similar to an encryption here, to the entire message, and we obtain a very long signature that is as long as the message here. So if you obtain a new version of your operating system, and the operating system is 1 gigabyte, you would not like that the digital signature is also 1 gigabyte. So in practice, you want the signature to be long enough to be secure, but short enough to be practically verifiable here. So therefore, we use a mechanism to transform a long message into a digest by applying what is called a hash function. A hash function is a generic term that is used in computer science to any function that takes a long message to make it short in a way that appears to be completely random. So if I take a long message of any kind, which is a text or an operating system code, and I transform it into a 256 bits digest, then it should be as if this digest is taken by choosing the sequence of bits completely at random, which is the same as flipping a coin for every bit and deciding whether it's 0 or 1. This is called a hash function. Hash functions are used in computer science everywhere to reduce the time it takes to access data in a big table, for example. But a bit like in error detection codes, any hash function is not necessarily a good one. It needs to be a cryptographic hash function in the sense that the hash function should make it should be impossible to create a false digest that corresponds to create a message that corresponds to a given digest, for example. A hash function is very similar like a MAC, but with a big difference. There is no secret. So a hash function takes a message and transforms it into a small block here. So it is this block that we will sign by applying, for example, RSA. So instead of signing the entire operating system code, you will sign only the hash, which is 256 bits, and will give you a signature, which is 256 bits. Here is an example of a hash function done by Homer. As you will see, it is not secure, but we can use the same mechanism that provides a good hash function. So if the goal is only to have the hash appear to be random in order to save size in tables, like we do in dictionaries in computer science, in Python, for example, then that is good enough. We could use it. And here is what I would obtain when I hash this message. I didn't sign anything because there's no key. I obtain F7 here. However, this is showing what happens if I take this original message and I've modified the part, I've modified the message here to obtain, for example, I've modified the recipient. I've changed the bank account number of the recipient. Of course, if I hash this, I will obtain a different value, 7.4, which was not the original value. F7 was the original hash value. But you can see that there is a trick here because such a hash function that is linear, so linear things can be easily manipulated. For example, here by inserting spaces, I've taken exactly the same message, but I've inserted spaces. And the space is a non-zero character. By computing the right number of spaces, I can obtain whatever hash function I want here. So if I am an attacker, a man in the middle, I could do the following: change the bank account number, add empty space things, and chances are the receiver at least if it's manual, if I'm really sending this via fax or something to somebody who reads it, chances are they would accept this. They would say, yeah, well, there's space here, but okay, for some reason, there's some spacing here. So that's an example of a hash function which is not cryptographically secure, in the sense that it is possible to forge a message in order to obtain a desired hash, which is what an attacker will do. When I change a part of the message, the hash must remain the same because it's the hash that will be protected by the cryptography. So I need to modify again the message to obtain a desired hash. So a hash function should not make this possible, and it should be collision resistant here. Hash function collision resistance is a difficult thing. In the past, there were hash functions called MD5 and SHA-0 that were for a long time believed to be collision resistant, and then somebody smart enough found a way to attack them. So we invented replacements for that are the family SHA-2 or SHA-3 that are considered to be secure today here. But again, we find the same take-home message that we had with AES. Before AES, there was DES that was believed to be secure for a long time. Then one day it was no longer secure. The same is true with your hash function. And we will use hash function when we use asymmetric cryptography for authentication. So if you use a hash function, you must make sure it is the most recent one, or the one on which there has been no security alert, which as a side effect will mean that we will need to be able to change our software. If I have a hash function and I add to my message a random number, so before I hash my operating system code, for example, I obtain a 256-bit code, then 256-bit hash value. I can pick a random secret of 256 bits, share it with the destination, and add it, XOR it to the hash. If we have this, we have obtained exactly a MAC. So a MAC, we have a second mechanism to produce a MAC. One is to use chaining with a block cipher system like we do with AES. Another one is to use a hash function and add a key, which is a random number here. Of course, this is symmetric. This secret key has to be shared with the destination. So don't confuse with asymmetric use of hashes here. Okay. One little quiz to check your understanding. PMU signs messages sent to PDC. For verification, the PDC should use which key? I close the poll in a few seconds. And the majority says A, which is the correct answer. The PMU signs with its private key. This is how we can have authentication. The signature has to be done with something secret. And the verification at the PDC uses the PMU's public key, which should be made public, or at least public within the domain that is used by this smart grid. A more tricky question here, so I'll let you discover the text. I'll come back to it in a second. I'll close the poll in a few seconds. That's a tricky one. The correct answer is H, which had 0 vote for it. Let's see. What is shown in this question is exactly the kind of things you see when you do a Wireshark, an analysis of an exchange of the messages that are exchanged when, for example, two systems use TLS or HTTPS, or when you debug the code in your smart grid to see what a PMU is sending to a PDC. So the first system, we say we have C, so this we use CBC AES-K of M. That means it's a crypto system, CBC AES. That's a symmetric cryptography system with a secret key K here. And here I'm saying, if I receive two ciphertexts, C and C primes, that are encrypted, no, well, I said something wrong. No, this is correct. I receive two ciphertexts encrypted with the same key here. Am I sure that the two messages, the plain text, are the same? I was tempted to say yes, and a number of you said yes, but this would be true only if AES. With CBC, we do the chaining. Remember, the goal of chaining is to avoid exactly this repetition. If I encrypt the same message twice, I will obtain different things. So conversely, if I get the same, I cannot be sure that the message was the same. So this is not true because of the nonce here. Then HMAC SHA-512K prime. SHA-512, that means that's how things are written when you read docs, or this is how software displays the system it's using. That's a SHA-2 system with 512 blocks, and it's an HMAC with a key. There is a key, so that means we use hash. This is the hash. It's a SHA-2 system, so it's secure. And there is a key associated. So as we said before, we choose a random key of 512 bits, XOR it with the hash, and obtain an HMAC system. So that's a MAC system, a bit like we saw with the AES MAC. But the MAC, of course, in general, will not guarantee that if the tags are the same, the messages are the same, because the tag is typically shorter. That's the message. That's the goal of a hash system, is to, M is perhaps the entire operating system code. So it is possible that different versions of the operating system gives exactly the same tag, because the operating system code is 1 gigabyte and the tag is only 512 bits. So much smaller number of bits here. Of course, you can say this is not secure because but the probability that if the hash is truly cryptographic, forging thing, the only way you can do it is by chance, and the probability that you are right by chance will be 2 to the power minus 512, which is an extremely small number, right? 512 you divide by 3 to obtain the number of decimal digits, so it gives roughly 200 zeros after the comma, so 10 to the power minus 160 or something, which is an astronomically small probability. It's the probability that that my chair is liquid at this time, for example. The same is true here. D is a hash. So here, SHA-3. SHA-3 is another version of SHA. I said there's SHA-2 and SHA-3. So SHA-2 is written usually in this form. SHA-3 is usually written in this form. D is a pure hash. There is no key. So it's just a hash of M. So it's purely predictable. Anybody can recompute it. But of course, you cannot invert it. That's the purpose of a hash. In particular, it's not one-to-one. There can be multiple M's that give the same D for the same reason as a minute ago. Well, this is the answers I gave. That will be printed in the versions of the slide that I will post after this lecture. We have seen how asymmetric cryptography does essentially the same as symmetric cryptography, but with one of the keys being public. In fact, one of the major uses of this is to do what we call certificates here. So here we start with the example we saw before. Lisa goes to the bank, obtains the public key of the bank, uses that to obtain a session key. In fact, there will be 2 session keys, one for encryption and one for computing the tag here. Here, if we use this encryption and MAC in parallel, then those 2 keys will be used to communicate with the bank. That's exactly what we saw under the name of hybrid cryptography. And this is what is used today in most HTTPS transactions. However, this is not completely safe because a man in the middle could intercept the communication and replace the public key of the bank by the public key of the bad guy here. So you talk to the bank, the man in the middle pretends to be the bank, sends you a public key, which of course is not the public key of the bank, but you can easily create your public key. In the lab TCP-IP, we do that. So you can have, if you're a bad guy, create a public key. And then what Lisa will do, she will encrypt with the public key of the bad guy the session keys. Now the bad guy will pretend to be Lisa for the bank. The bad guy will first decrypt the private session key, the secret keys, using its private key. Of course, the bad guy knows its own secret key, and then we'll do the same thing as Lisa did with the bank before, but the bank has no idea whether this is coming from Lisa or from a man in the middle here. And when Lisa says transfer 2 million to B0, then, and verifies that with a MAC, checks that, signs that with a MAC, then the bad guy will decrypt everything, changes all the MAC, and send the thing to the bank. Well, to the bank will appear to be correct here. So that's a man-in-the-middle attack. That is a possibility and a possible attack against hybrid cryptography. What was it? Why was it possible? Well, the problem was that Lisa trusted the public key here to be that of the bank when it was not here. So that's one of the first things we learn on this example. When you get a public key somewhere, that is a very, very, very serious thing. you should think twice before accepting that something is the public key of some organization or some person here. So accepting a public key is something that may lead to attacks here. So we should authenticate the public key. But since we use public keys to authenticate, we have a chicken and egg problem here. So how can we solve this? Well, like any chicken and egg problem, it is solved by having an initial hen that produces the very first egg of history. And this is what we do here. And this hen is the certificate authority. So a certificate authority is some organization whom we trust that issues signatures that will be trusted by everyone. Those signatures are applied to what is called digital certificate. So what is a digital certificate? It's a piece of text that contains the identity and the public key of some organization. For example, here is how a certificate of Lisa's bank could be. It contains text about who the bank is, where it was registered, in which country, and importantly, its public key here. So it contains the public key, and this needs to be verified. So it is verified by being signed with the private key of the certification authority. So the certification authority has a private key. There are a number of certification authorities, companies like Global Sign, for example, are. And then of course, they should keep their private keys very, very secret. And the public keys of those, of course, must be known. How they will be known, we will discuss in a second. So when Lisa receives this certificate, she receives not just the public key of the bank, but she receives a certificate that is signed by Global Sign here. Now the browser, Lisa's browser, will verify the signature using the public key of Global Sign. Now, how is the public key of Global Sign securely transmitted to Lisa? Well, this is where the origin of trust in the software of Lisa is in the browser. So when you buy a computer or you install an operating system of a computer, you should install not just the operating system, but the browser that comes with it. If you use a Windows computer, you should have Microsoft's Edge or Explorer. If you use an Apple computer, you should have Safari. And with this browser come pre-installed public keys here. So we trust the initial installation of our system. This is why the initial installation of a system is very important. It should be done in a certified way. So if you receive your computer for the first time, you should have a hard disk or some mechanism to verify it that comes shipped with the computer. So typically, if you buy a fresh computer, it has a version of the operating system already installed on the hard disk here. Those certificates have a validity time and can also be revoked. The validity time is because something that is secure today might not be secure in the future. This is also why computers need time. If your clock on the computer is wrong, if your computer believes we are in 1961, then your computer might very well accept a certificate that is out of date. So time is important also for security. Browsers should always verify the validity of certificates, but there are many browsers, in particular if you have self-installed browsers, some you may need to check whether everything is done in a really secure way here. So for example, many users install Chrome on their computer. If you have a Windows or a Mac OS, it will not come with Chrome pre-installed. It will come with the native browser of the operating system. But the installation of Chrome will be verified by your computer using the keys pre-installed with your OS original version. So Chrome is a very secure one. Others might not be as secure. What does Lisa's browser obtain from the digital certificate for her bank? I propose you a number of possible answers. What do you think? I'll close the poll in a few seconds. And the majority says D, which is the correct answer. The goal of the certificate is to obtain the public key of the site that you're connecting to. So this will be, of course, there. The public key, of course, is not useful if you don't have information about it. So typically you may want to give a little information that comes in the form of a logo, for example, that can be quickly used to see, to check whether what you see corresponds to what you expect. The public key of the issuing certificate authority, of course, you should not get it from the certificate, because if you do that, that defeats the purpose of a certificate. So the correct answer is D. The public key of the certification authority should be pre-installed in your computer, perhaps by going to sites through an indirect, through a number of steps, but it should not be in the certificate. Although there exists one thing called self-signed certificates that contain the public key also to be used. And unfortunately, it is possible that you receive a self-signed certificate and your operating system, if it's not very secure, might say, do you accept this certificate? Well, accepting such a certificate is like not having a certificate. Right. So unfortunately, that happens, but this does not make sense from a security viewpoint. The last topic we need to see is forward secrecy. So most cryptographic systems today used something a little more complicated than what we've seen, which is called forward secrecy. What is the problem? Well, we've seen that we typically use hybrid encryption, which uses a combination of symmetric cryptography for the session with encryption and tags, asymmetric cryptography to create the session keys and exchange them in a secure way, and asymmetric cryptography again to make sure that the public keys that we obtain are secure. So this is how all things are stacked together. However, this might not be sufficient. Assume an adversary records all messages sent at some time. Sometimes later, 5 years later, for example, the private keys that were used when this message was sent, so the private keys of the crypto system, for example, the RSA key of the bank, is revealed. Well, can that happen? Well, yes, for some reasons. For example, once in a while, we hear that a big organization has lost one of their secret keys. Something that is secret was revealed by some security breach. So nothing's perfect and security can never be absolute. So it is possible that an accident happens and the key is revealed. Worse, it could be, for example, that you are using RSA with a key of 256 bits, which can now relatively easily be broken with a cluster. So it is possible to, through advances in cryptography, cryptanalysis, to break something that is not breakable at a given point in time. And we've seen that's a constant in cryptography. Whatever is secure today might not be secure in a few years from now. So now assume you're the attacker. You've recorded this, you kept it, and now you have all the messages that were exchanged, including the encryption of the session keys. Therefore, I can decrypt all the session keys and I can get all the secret information that was exchanged during this exchange of information here. If that happens, we have broken what is called forward secrecy. So forward secrecy means that an adversary who has been able to copy the messages sent in the past and in the future, presumably, obtains the private keys that were used at the time where those messages were sent. Well, the thing is forward secret is even obtaining this, we cannot decrypt the logs of the messages here. So why do we care about this? Well, it is because, well, first, something that was exchanged here might have been confidential. And perhaps if it's a message of the government, perhaps even 5 years later, we still want it to be secret. So we would not like to reveal secrets that have some impact on the world and on people here. Also, among the secrets, there might be things like passwords. If you do what I recommend, which is to use password managers and change your passwords frequently, then you will not be exposed to that. But not everybody does that. So chances are there will be some people that will have the same password. So if you're the attacker, you have a database of possible passwords and you will use a computer to test all of them on all the systems, and chances are you will succeed and gain access to some systems. So that's the problem that we want to solve, and this is why most crypto systems today use a solution to that. The solution is based on what is called Diffie-Hellman key exchange. This is one of the possibilities here. Here is how it works. It's again using the same trick of cryptography, which is using finite fields or some exotic algebraic framework. Here I'm showing a scheme that uses modular arithmetic here. So here, A and B agree on a very large prime number, capital N, that is public, and a number G, which is called a generator. What is a generator? Well, a generator with respect to a large prime number is a number such that all the powers of G, modulo N, gives all possible numbers between 1 and n minus 1. So number theory tells us that for any prime number n, there is at least one generator here. So G and N are public. Given a message M, computing G to the power M is easy. That's something we've discussed already. Even in modular arithmetic, computing a power of a fixed number is not a difficult problem. However, here is another difficult problem. We've seen a first difficult problem, which is large integer into its prime factors. Another large difficult problem is given G to the power of M modulo capital N, where N is a prime number, given G that is known, finding M, finding the exponent is difficult, is believed to be difficult. So finding the exponent when you know G to the M, that's the inverse of the exponentiation function. So in usual arithmetic, if we use usual real numbers, that is called the logarithm. If I give you 10 to the power some floating point number, 10 to the power 03973, etc., then I can compute it easily. Reversing that is computing the log of the result. So by analogy to that, we call it the discrete logarithm. It has nothing to do practically with the logarithm, so you don't use log tables to compute it. Computing the log is believed to be a hard problem, and the only known solution is brute force. You compute all the powers of G to the power M of G, and then you look up the table to find which gives you G to the power M. Of course, all this trick will work if capital N is a huge number. If N is 2,000 bits, then you have 2 to the power 2,000 possible things to search for. So that's a huge, more than astronomical number. So it will require all the computing power of the world for a long period of time before you can find the solution here. So we believe that is a secure way to do here. It's a very hard problem. Given that, how does it work? Well, remember, G and capital N are known and public here. So Lisa will choose a number randomly. So again, we assume there is a random number generator here, and this will be kept for a given session. And Lisa will compute G to the power A. Remember, G is public. Of course, when I say G to the power A, is G to the power A modulo N. And she sends this to the bank here. So any opponent will see G to the power A. And because we believe it's very hard to do the discrete log, having G to the power of A doesn't tell us what A is. The bank will do the same and choose another number, which we call B, and send it to Lisa. And then what will Lisa do? she will compute the number received from the bank to the power A. Remember, computing something to a given power is an easy problem. So she will compute a number L. And the bank will do a similar thing. The bank will compute G to the power B to the power A. And again, because we have a commutativity of those two operations, G to the power A to the power B is equal to G to the power B to the power A, which is G to the power A times B. So the bank and Lisa will have the same secret number, L. But any opponent, any adversary that has found G to the power A and G to the power B doesn't know A and doesn't know B. So it is impossible to compute G to the power B to the power A. In order to compute the secret, I need one of the two numbers and the log of the others. But we believe computing the log is practically unfeasible here. So after having done this, the bank and Lisa have a secret number. Having the secret number, they can use symmetric cryptography. Here is how it works. To understand, we use, of course, very small numbers. This is not cryptographically secure because a brute force attack will find them. Here I use as prime number 17. You can verify easily it's a prime number. And the generator is 3. The generator is 3 means if I take all the powers of 3 for any possible value of k, and I take this modulo 17, this is the computation I did here. For example, 3 to the power 1 gives 3. 3 to the power 2 gives 9, etc. 3 to the power 5s will give me 3 to the power 2 is 9. 3 to the power 3 is 81. And 81 modulo 17 is 10. If I divide 81 by 17, I find a remainder equal 10. I continue this, I obtain all those values here, and we see here that we have a one-to-one mapping for all values except 0. We don't find 0, of course, because by putting something to a power, we don't obtain 0 when we have a prime modulus here. But I obtained all the numbers. That's why it's called a generator. Of course, the order appears to be completely random. That's the beauty of this theory. For example, if I ask what is the discrete logarithm of 7 in this modulo 17 arithmetic, the answer is it's 11. But the discrete log of 5 is 5, the discrete log of 6 is 15, etc. So it is, in principle, it appears to be completely random, which is what it means when we say it's impossible to crack it other than by brute force here. So A will choose a random number, for example, 7. We'll compute 3 to the power 7, so 7 that gives 11, and 11 is what is sent to the bank. The bank has chosen 13 and sends 12, and having received 11 and 12, if we know how to reverse to compute discrete logarithms, of course, we have broken the scheme, but here we don't. Lisa will compute the received number, 12 to the power 7, 7 which is her secret number. She will obtain 7. 12 to the power 7 gives 7. You can do the maths, and you will see the remainder is 7. Similarly, 11 to the power 13, 11 is the number received, 13 is the local secret number, will also give 7. So both have agreed on 7 with 0 exchange of secret information. So that's an example of managing to obtain a shared secret without sending any secret information online here. As with RSA, it requires the prime number to be very large, and similarly as with RSA, a variant using elliptic curves works with much smaller numbers. But all of those things work as long as quantum cryptography doesn't work. If quantum cryptography works, we need to replace all those crypto systems with other ones which are more heavy to use but are more secure. It's called lattice cryptography. What I presented seems to work, but in fact, there is still a problem. It is still susceptible to man-in-the-middle attack here. Exactly the same as we saw before when we did not use certificates. We see that if a man in the middle pretends to be the bank to Lisa and pretends to be Lisa to the bank, then that man in the middle will be able to break it. because that man in the middle will send an information, will pick its random number R for Lisa and to the bank, and will obtain the secret key to speak with Lisa, will obtain a secret key to speak with the bank. Lisa believes she speaks with the bank, and the bank believes we speak with Lisa, but both are speaking with a bad guy that has all the keys to decrypt everything, and therefore can change all the messages and read all the messages. So we break confidentiality and authenticity here. So of course, this doesn't work. But the same solution that was used before can be used to prevent this. Then we use a system of certificates. So the same problem is solved with the same solution. So here is in practice how hybrid encryption with forward secrecy is used. We use signed Diffie-Hellman key exchange. So how does it work? Well, first, Lisa chooses a random number A, computes G to the power A, like before, but signs it with her private key. Similarly, the bank will do the same thing, will create a random number B, compute X prime, G to the B, and signs it also with the bank private key. So here we see that both need public and private keys of both here. When both have obtained this, then they have obtained something that is truly guaranteed to come from the other end. So the man in the middle will not be able to sign with the private key of the bank. Therefore, Lisa will verify it with the public key of the bank, which she has obtained from a certificate. Now, the bank needs also to have the public key of Lisa. So there needs to be a prior exchange of information between Lisa and the bank, which is probably what you do when you have some installation of contract and software with your bank here. After this is done, then the system is the same here. So the keys A, B, and L are random and temporary. Temporary because any crypto system, even like AES, over time, if an attacker has seen a large number of messages, we're not sure today whether it cannot be used to leak some information. Therefore, we prefer to make that temporary and short-lived here. And an adversary who has access to the history of the messages cannot decipher the message, even if she finds the permanent key stored at the bank. Even if those private and public keys are stored here, then she will not be able to revert this thing here. So forward secrecy, as we want it, will be enforced. Voila, this is what forward secrecy is. A quick question to check your understanding. I close the poll in a few seconds. And the majority says C, which is correct. So the beauty of Diffie-Hellman key exchange is that you create the same secret without ever exchanging anything secret online. But B is unfortunately true. If you can solve the discrete logarithm, then hybrid encryption is not forward secret. Forward secrecy relies on the fact that the keys that are used for encrypting the information are temporary and completely random. and are not kept in the logs. If you see the messages, the logs of the messages will not contain the keys. That's because of point A, they were never exchanged. And if you gain access to the private encryption keys that were used, like my public key, my private key, sorry, or the private key of the bank, you still don't know what is the random number that was chosen to create this session key. So the fact that the keys are temporary and random is what makes the thing forward secret. However, if we can break the discrete logarithm, we have seen the g to the power a from which we can get the a, and therefore we can get the secret keys here. So whenever quantum computers will be available, all forward secrecy will disappear. So hopefully the industry will move to lattice cryptography a bit before quantum computers become available. Voila, that's the end of this session and this module. Quick recap: encryption provides confidentiality. MAC provides authentication using a secret key. Public key cryptography and certificates provide authentication and non-repudiation. And I recall and repeat, a cryptographic method that is secure today will very probably not be so in a few years. Therefore, software must be regularly updated. Password must be frequently changed, must be different for every authentication system that we have. And how do we manage all this? Well, there are authentication sites sponsored by governments like NIST in the US, similar sites in Europe that provide all the recommendations about which system is secure and which not. And whenever you use software that's a bit old, you're taking the risk of having unsecure parts of it. Which means that in the context of smart grid, as soon as we computerize a system, as soon as we make it connected to the outside, we must pay the burden of updating the software quite regularly. And many problems that occurred in the past were due to the non-awareness of this fact.